We live in a world that feels predictable. A ball falls to the ground, light travels in straight lines, and objects move when pushed. These are the laws of classical physics, simple, logical, and comforting. But the moment we zoom in, to the levels of atoms, electrons, and photons, everything changes. Suddenly, the rules stop making sense. At this scale, particles can act like waves. They can exist in two places at once. They can even affect each other instantly, across vast distances. This isn't science fiction. This is quantum mechanics. Quantum mechanics is the branch of physics that describes the universe at its most fundamental level. It's not just a theory, it's one of the most tested and confirmed frameworks in science, and yet it's also one of the most mysterious. It forces us to question everything we thought we knew about matter, about energy, about space, time, and even reality itself. But why was it needed? Because classical physics, the physics of Newton, of gravity and motion, started to fail. It couldn't explain the behavior of light, or why atoms didn't collapse, or why energy seemed to come in small, discrete packets. So scientists had to dig deeper. They had to go beyond what was visible. They had to let go of common sense and enter a world where reality behaves in a strange and beautiful ways. This world is governed by principles that defy intuition. A particle can be in a state of multiple possibilities until it's observed. Two particles can be connected so deeply that one feels what happened to the other instantly. And there is a limit to how much we can ever know about a particle, not because of our tools, but because of how reality actually works. These are not just ideas, they are proven, and they have built the foundation of modern technology, from lasers to computers to quantum computing. So in this video, we are going to explore the core ideas of quantum mechanics, not with equations, but with clear explanations, not for physicists, but for curious minds. We will uncover the real meaning behind terms like superposition, entanglement, uncertainty, and more. By the end, you will have a fair understanding of what quantum mechanics is really about and why it changes everything. Let's begin. To understand quantum mechanics, we first need to go back in time to a point when classical physics ruled everything. In the 19th century, scientists believed they had figured it all out. Newton's law could describe motion. Maxwell's equations explained electricity and magnetism. Everything seemed smooth, continuous, and predictable. But then, cracks began to appear. The first problem came from something as simple as light. According to classical physics, when you heat an object, it should keep glowing brighter and bluer forever, pouring out infinite energy. But in reality, that didn't happen. Objects glow red, then orange, then white, and then stop. No infinite energy. This problem was called the ultraviolet catastrophe. To solve it, in the year 1900, a German physicist named Max Planck made a bold move. He proposed that energy doesn't flow continuously. Instead, it comes in tiny fixed packets. He called these packets quanta. It was a radical idea that energy is not smooth but quantized. It worked. His formula matched the experimental results perfectly. But even Planck didn't fully believe what he had discovered. A few years later, Albert Einstein took this idea even further. He studied the photoelectric effect, an experiment where light shines on a metal and causes it to release electrons. Classical theory said it shouldn't matter how strong or weak the light is. It should always eventually knock electrons out. But that's not what happened. Only light above a certain frequency could eject electrons, no matter how dim it was. Einstein explained this by saying, light itself comes in packets. In particles, he called them photons. This was shocking, because light was always thought to be a wave. So now light, something we thought we understood, was behaving both like a wave and a particle. This was the beginning of a revolution. Next came Niels Bohr, who tried to explain the structure of atoms. Classical physics said that electrons orbiting a nucleus should quickly lose energy and spiral into the center. But that doesn't happen. Atoms are stable. Bohr used Planck's idea of quantized energy to say electrons can only exist in specific orbits or energy levels. They can jump between these levels, but not exist in between. This explained atomic spectra, the specific colors of light emitted by elements. One by one, these strange discoveries were building a new picture of the universe, one where energy is quantized, light is both wave and particle, and atoms behave in ways classical physics could never explain. These early breakthroughs laid the foundation for a new theory, a theory that would explain the rules of the microscopic world. That theory is quantum mechanics, and from here, things only get stranger. Now that we have seen how quantum mechanics was born, let's talk about one of its most mind-bending ideas, wave-particle duality. This concept tells us that tiniest things in the universe, like light and electrons, can behave both like particles and like waves, not either or but both, depending on how we observe them. Let's start with the light. For centuries, scientists argued over what light actually is. Some said it was made of particles, others believed it as a wave. Then in 1800s, experiments like Young's double-slit experiment showed that light creates interference patterns, a behavior only waves should show. That settled it, or say the thought, light was a wave. But then Einstein came along with the photoelectric effect and proved that light also acts like particles, photons, tiny discrete packets of energy. So now we had a strange truth. Light is both a wave and a particle. But it didn't stop there. Later, scientists like Louis de Broglie proposed something even more shocking, that matter also has a wave-like nature. Not just light, electrons, protons, even atoms. All of them could behave like waves. To test this, physicists fired electrons, tiny solid particles, at a barrier with two slits. They expected the electrons to behave like tiny bullets, forming two clusters on the screen behind the slits. But what they saw was different. The electrons formed an interference pattern, just like waves would. It was as if electron passed through the both slits at once, interfering with itself. Even stranger, when scientists placed a detector to see which slits the electron went through, the interference pattern disappeared. Now they behaved like particles again. Just watching the electrons changed how it behaved. This experiment, the double-slit experiment, remains one of the most famous and puzzling in all of science. It shows that particles have a dual nature. When left alone, they act like waves, but when observed, they act like particles. It is as if nature responds to our curiosity. Wave-particle duality isn't just a trick or illusion. It's a fundamental property of reality. It applies to electrons, protons, atoms, even large molecules. In theory, it applies to everything. It's just that the wave-like behavior becomes harder to detect in bigger objects. This duality is at the heart of quantum mechanics. It challenges our intuition and forces us to rethink what it means to be something. Is an electron a thing or a vibration or a probability, or is it all those at once? If wave-particle duality wasn't strange enough, quantum mechanics take us even further, into the realm of superposition. So what is superposition? It's the idea that a quantum particle like an electron doesn't just exist in one state. It can exist in multiple states all at once until it's observed. Let me explain. The classical world, if you flip a coin, it's either head or tail. Even before you look at it, you just don't know which one it is until you check. But in quantum world, things are different. A quantum coin would be both heads and tails at the same time. Not because we don't know, but because that is actually state. It's in a combination, a superposition of all possibilities, and only when we measure it does it choose one. This idea sounds impossible, but it's real. It's been tested again and again. Electrons can be in more than one position. Photons can take more than one path. Even atoms can exist in superpositions of different states of energy. This leads us to one of the most famous and strangest thought experiments in physics, Schrodinger's cat. Imagine a closed box. Inside the box, there's a cat, a vial of poison, a radioactive atom, and a detector. If the atom decays, completely random and unpredictable, the detector triggers the release of poison and the cat dies. If the atom doesn't decay, the cat lives. Now here's the weirdest part. According to quantum mechanics, until we open the box and look, the atom is in a superposition, both decayed and not decayed, which means the cat is also in a superposition, both alive and dead at the same time. It's not that the cat is half dead, it's that it exists in two realities until we look. Only observation collapses the superposition into one outcome. Schrödinger, the physicist who proposed this idea, didn't mean it literally. He was trying to show how strange the implications of quantum mechanics are when applied to everyday objects. But here's the truth. Superposition is real. It's the reason quantum computers work. It's the reason particles can interfere with themselves, and it challenges the very meaning of reality. Is the world around us definite, or is it a web of possibilities waiting to be observed? Quantum mechanics doesn't give a clear answer. It just shows us that nature at its core plays by rules far beyond our everyday science, everyday experiences. Now, let's explore one of the most mysterious and magical ideas in all of quantum mechanics, entanglement. Quantum entanglement is a phenomenon where two or more particles becomes deeply connected, so much so that the state of one particle is instantly linked to the state of other, no matter how far apart they are. It doesn't matter if they are a few centimeters away or on opposite sides of the galaxy. Change one and the other changes instantly. It's not just fast, it's instantaneous. And that's what makes it so bizarre. Even Albert Einstein found this idea hard to accept. He famously called it spooky action at distance. Why? Because it seemed to violate everything we know about how informations and causality work. Nothing is supposed to travel faster than the speed of light, and yet entanglement seems to do just that. So how does it work? Let's say you have two particles. Let's call them A and B. You have set them up in such a way that their properties are entangled. For example, if particle A is spinning up, particle B must be spinning down. But until you measure them, neither of them has a different spin. They exist in a shared superposition, both up and down at once. Now let us separate these particles by a vast distance. You measure particle A, and instantly its spin becomes up, and that exact moment, particles B's spin becomes down. It's as if the particles were still connected, no matter the distance. But here is the weirdest part. There is no signal being sent. There is no hidden message. It's as if reality itself is a non-local connected in ways that transcend space and time. This has been tested again and again in experiments, and it's real. Entanglement is not just a theory, it's a measured, confirmed phenomenon. But what does it mean? Some scientists think that entangled particles aren't two separate objects at all, but rather part of the same system, even when separated by distance. Others suggest that our understanding of space, time and causality might need to change, that the universe at its core is deeply interconnected in ways we can't yet fully grasp. And here's the crazy part. This isn't just a philosophical idea. Quantum entanglement is the foundation of quantum computing, quantum encryption and quantum teleportation. It's opening the door to the technologies that were once science fiction. Entanglement forces us to rethink what it means for two things to be separate, because at the quantum level, separation might just be an illusion. As we dive deeper into the quantum world, we come across a principle that flips one of our most basic beliefs upside down. The belief that we can measure anything as precisely as we want if we just try hard enough. In the quantum world, this belief breaks down. Welcome to the Heisenberg's uncertainty principle. This principle, discovered by Werner Heisenberg in 1927, says something truly astonishing. There are certain pairs of physical properties that you can't know exactly at the same time. The most famous pair is position and momentum. The more precisely you know where a particle is, the less precisely you can know how fast it's moving, and vice versa. This is a limitation of your measuring tools. It's a fundamental limit of nature itself. It's not that the particle has a different position and momentum and we can't just see it. No, the particle does not have both the values at the same time. That's a shocking part. At the quantum level, particles don't have exact locations or speeds. They exist as probability clouds. There's a chance that they are here, a chance they are there, and only when we measure them do we find out where they are and collapse the cloud into a result. Now let's take it one step further, into a phenomenon called quantum tunneling. Imagine a ball rolling towards a hill that's too steep for it to climb. In the classical world, the ball would just roll back down. But in the quantum world, something bizarre can happen. Because particles are not just in one place, but spread out as waves of probability, there's a small chance that the particle's wave extends beyond the hill. And that means occasionally it can tunnel through the barrier, even if it doesn't have enough energy to climb over it. It's like magic. A particle simply appears on the other side. But this magic is real. It's been observed, measured, and even used. Quantum tunneling is the reason nuclear fusion happens in the sun. It's how electrons escape atoms. It's the principle behind the devices like tunnel diodes and scanning tunneling microscopes. It reminds us that in the quantum world, what's possible is never just black and white. It's a world of probabilities, where particles can vanish from one place and reappear in another. All because the rules of nature allow for it. The uncertainty principles and quantum tunneling both show us something powerful. Reality at its deepest level is fuzzy, unpredictable, and full of surprises. And somehow it all still works.